So for this example, we want to show that the phrase P or not Q is equivalent to not P implies not Q. So if we want to see that two statements are equivalent, what we want to do here is make truth tables for them and then carefully go through the steps here to see that they refer to the same truth in the same way. That is, they have the same truth values regardless of which conditions we throw at them for their component simple statements. So we're going to start here like we always do with our options for the simple statements P and Q. True, true, false, false, true, false, true, false. Then, because we need not Q for both, I'm going to make not Q. So you just flip all the values, false, true, false, true. Then you look at P or not Q, where in the first case, P is true, so P or not Q is true. In the second case, both are true, so the disjunction is true. In the third case, both are false, so the disjunction is false. And then in the last case, not Q is true, so the disjunction is true. Not Q is true is a hard phrase. But anyway, the next thing we're going to look at here is the negation of P. So flip that, becomes false, false, true, true. And then we look at the implication there of not P into not Q, which unfortunately is written a little bit backwards on our table. We're just going to be careful at how we read this, that in the first case, not P is false, so it doesn't matter what happens to not Q. Similarly, get the same thing in the second case. Then in the third, we have that not P is true and not Q is false. So that means our implication there, our conditional, must be false. And then for the last case, both are true. That is our best case scenario for a conditional to be true. So looking at our two columns in total, we have that they are true in the first two cases, false in the third, and true in the fourth. So it's very important when we see these things to understand that this order does help us clarify about what's going on there. That's kind of why you want to keep that consistent pattern with the P's, Q's, and R's in terms of twos, like I mentioned way back at the start. This helps for being able to see equivalence in particular. And in this case, we do have that these statements are true at the same times. That is, the same components being true makes the total thing true as well. And as a result, we say they are equivalent, where we denote this by saying P or not Q is equivalent using a three-lined equality. This means is equivalent to not P implies not Q. So just to be sure, this right here is read as is equivalent to. That's specifically what that symbol means, at least in this context. Generally, that is what it refers to, but it's important to be specific here as well. And for another very simple example of equivalent statements, the most obvious example there is, we can think about what happens if we take a negation, not P, and negate it again. That, for hopefully obvious reasons, because we're flipping truth value twice, is equivalent to the original statement, just so we have a little bit more comfort with what this sort of notation refers to with an example. It's a little bit less clear, but that we have arguments for, and then something that's pretty clear that we shouldn't need any more logic to understand. Anyway, that's how we define equivalence. That's what we look for when we want equivalence. So let's return to that example that we had earlier and think about how we can change conditional statements in the context of which ones refer to the same truth, but maybe in a different way.